once again. Hello, Jared. Hello, Spencer. Hello, Kennedy. Hello, Tim. So Jared is online, and we have an absolute majority in the online. And hello, Zain. So if you want to say hi to Zain, you can show your cameras. So what are we going to do today is pretend that we do not have computers. I know it is kind of silly exercise, but we were doing interesting. Okay. We were doing productive and interesting things by answering our scientific questions, like what would happen with electron injected in the box if it hits the walls, with the MATLAB code. And we were using benefit of us being in 21st century. But what if we would be like 100 years ago is too early, like 80 years ago, 70 years ago, quantum theory was already developed, but there were no computers. So, or what would we do as a homework if we wouldn't get MATLAB exercise? So I will demonstrate it and invite you to follow and look on some things, but it will be not a homework. So you'll just see how happy we are that we are not doing it for points. Someone told something in the chat. Good morning, Spencer. Yeah. Okay, I'm going to share screen and probably focus on instructor, who is myself today. Share screen, editing, start presenting. So we are in the middle of the chapter on the particle in the box. Here is the homework, which is due coming Monday, and I'm not very good in counting dates. I think it will be 12th. Sure. But do not look on me and on the dates. Just submit on the Monday. And if you are watching recordings or attending the web, it is like 5 minutes effort. Okay, 10. So here is our navigation map, and my personal goal is to bring slides in the whole course in this format. But you will see, if I am behind my own schedule, from time to time you will see the similar style map, which is with other hand drawing. So we are using density metrics to predict dynamics of electron in one-dimensional box. Equations at the bottom is something that would be great if you memorize. If not, I would not reproduce them in the middle of the night. I would just rewrite them. So we are exciting electron from the ground state with n equals 1, which is matching boundary conditions, and it is like a camel with one hump into the camel of two humps, but not completely 50%. And looking how things are changing in time. So in the previous meeting, we did introduce the concept of so-called density metrics, which is an auxiliary tool in order to get distribution in space, and second, in order to get observables. So what we define as density metrics is just combination of expansion coefficients of wave function, including their time dependence. So when we need dependence of position in space, we can separate dependence on space, which is just product of eigenstates, and dependence on time, which includes initial conditions and phase accumulation of each eigenstate. And if you multiply two exponentials, we get the subtraction here. And from this equation, we see if it is density matrix for the same indices, I this energy subtract, and we get no time dependence. So a little ugly angular symbol here is Greek sigma, which symbolizes summation. Just please. So if we practice this stuff, we arrive to the following equation for the evolution of probability distribution of this superposition wave function, which was our interest. We were interested to see how it bumps into the wall, how it reflects back, and we saw that it is quite easy in minimalistic scientific computation. Now we're going to get these same images by pen and paper, pretending that we are ancient scientists. So initial coefficient, time dependence, spatial part. Initial coefficients, time dependence, spatial part. This is for, I do not know how to draw camels. It looks more like a frog. So ground state, excited state, and then superpositional states. So initial combinations of initial conditions, time dependence, E1 minus E2, and we can call it delta E with minus sign because E2 is bigger than E1, and spatial dependence. Then another cross element, initial conditions, time dependence. Here we have E2 minus E1, which will be positive, and then spatial dependence. And here it is symmetric. If it is not quantum operators but functions, we can do old school swapping, no problem. And each of these terms formula has two indices, and we are doing summation over index I and over index J, each a number running from 1 to 2. So basically what we need to do is to evaluate this equation at different instants of time, and then add together 4 trigonometric functions, actually 3 because this one can be put out of bracket, and look on the answer. Make sense? So we are taking this stuff out of bracket, and due to our old body Euler, we are contracting 1/2 exponential accumulating phase in forwards and backwards as cosine. According to Euler, it is 2 cosines, but from initial conditions we have L1/2 and it cancels. If you were looking what is wrong in the code, if you were looking how to correct it, I think this stuff was missing there. And therefore one gets the expectation value in some versions of the code 2 times different from what it should. So cosine of time, and here we have sines of position. I hope everyone believes in Euler. I do not need to advocate it. So what is going on? First 2 terms do not change in time. Certain force, which we will call third, changes in time from -1 to +1. And depending on the value of the cosine, which can be -1, 0, or 1, we add these trigonometric functions with like different factor in front of it. And then we just need to practice boring high school trigonometric equations, right? So what else? When cosine will be equal, when the argument of the cosine will be equal pi. When, so we solve this delta E over h bar times t equals pi, and we can solve for time, it will be h bar pi divided by delta E. If we need 2 pi, just add 2, it will be a period of oscillations. So the smaller the energy offset, the bigger is period. Right? So let's look on this. So until the end of today's meeting, we will do nothing except analyzing this equation and trying to plot it. So let's look on the elements of density matrix, which are time dependent, at different instants of time. When time is equal 0, quarter period, and half period, just to scan opposite direction, because everything else will be in between. So if you have 0, pi over 2, and pi, you have different values of cosine. So let me invite everyone to go online. And start filling this table. So ideally on the paper we have how many? 8 registered members of the team, and I am number 9, and there are 9 empty spots in this table. So where is the text box? Okay. Text box. So at time 0, row 1 will be 1/2. So I'm done with my part. So now let me invite you to fill the thing. And I will fill, since I see only 4 online and Zain will be 5th, I will try to fill more cells which are trivial to induce you to, someone is, okay. So you see that for row 1 and row 2, it's quite trivial. There is only one cell left, rush to fill to make your contributions there. So cosine 0 is 1, yes, okay. And you have only one. Which one you were?
It was P22 times 0.
Okay, okay. And we have only one, yes, someone is writing in half period, cosine pi equals -1. Okay, yeah. Thank you very much. All participants will get a little credit for playing this game together. And now you see what we are going, everything is perfect. So we completed values for 3 time steps, 3 time slices, 0, quarter period, and half period. And you see the only difference is in this row 1, 2 plus row 2, 1. 1, 0, and -1. Thank you. I'm going back to the slides. And previous year, students were filling it just by scratching it on this touch screen. And 2 years ago, they were doing the same. And 3 years ago, they were doing the same. I think everyone likes it. Do not look on it. In previous year, I was so much slower than 50 minutes expired about this time. So when we add things together, we need to practice trigonometric things, and in few slides later, I will have it typed as real equations rather than other scratching. So this is row 1, this is row 2, and this is row 2, 1 plus row 1, 2. And then we have special parts. So each of the special parts does have something in common. So one can expand the sign of double argument as 2 sine times cosine, right? And one can do it, and then here is the square. So we will have sine squared and cosine squared. And in the last term, we have sine, and then sine of double argument, which we can also open as sine of the single argument. And then in each term, we do have sine squared here, sine squared here, sine times sine, so sine squared, which we can put outside of the bracket. And inside the brackets, we have 1/2. 2 squared will be 4, divided by half 2, cosine squared of single argument. And from here, if I do not do errors, it will be 2 cosines by x. So we need to practice this trigonometric equation and plot it. So you just lean back and relax, and think how happy we are that we do not need we do not do it for the grade, and only myself will mumble these boring equations which you do not need to do. So time 0, quarter period, half period. Sine square 2 sine times double sine, and here we have 0, and here we have minus. Maybe one can consider at 0.5 period to identify this as full square. A square, B square, 2AB. Maybe it will be easier to combine them. And then if it is possible, then if it will work out, then at half period, it will be just subtraction. Okay, let's see what I was doing in previous years. Okay, so identified full square, expanded sign of double argument onto 2 sine and cosine. Then placed sine squared out of bracket, and then left with 1 plus 2 cosine pi x over L. Do you believe me? Okay, so because of the square, this and this can go out of bracket. So this one is ready for plotting. In the middle one, we can also expand sine of double argument and put sine squared out of bracket. And inside the brackets, if we remove this sine squared, then you will have 1 plus 4 cosine squared. You still do it. Thank you for your trust or for checking everything. And through the course, everyone who finds errors, please disclose them and for extra credit. You help me and you help next generations. So here again, expanding sine of double argument, and then you have sine squared out of brackets and inside brackets 1 minus 2 cosines of single argument overall squared. So from now on, my task is to plot these functions without graphical calculator and without computer. So how do we plot functions? So if you live 80 years ago, of course, one can plug in each value of x and try to plot it, but it is so boring and it's very exhausting. We can do approximately. So in order to plot functions, one may want to find where the function crosses x-axis and where it is positive and where it is negative. And then the rest can be done just artistically, without much precision. Maybe evaluate where it is approximately taller, approximately lower, but basically finding zeros and signs is very good for qualitative analysis. So 3 functions. First one, snapshot at time 0. So cosine over the half period because I'm going, x goes from 0 to L, when x equals L, the argument of cosine equals pi. So it goes half period. Cosine changes from +1 to -1 as we go. And we have factor 2 right here. So this function in the yellow circle goes from +2 to -2. Make sense? Okay. Now we need to +1, which will mean that we just move everything up. And then somewhere shifted to the right from the middle, it will cross 0. Make sense? Okay. So now we take squared. So where it was 0, it will stay 0. Where it was positive, it will be positive. Where it was negative, it will become positive. So we are getting this shape. So we are done with this part. And now we need to multiply this blue thing times sine squared. So sine squared is this little green stuff. So the x goes from 0 to half period. Sine goes from 0 then to 1 to back to 0 at half period. And when we get squared, it just makes a little bit shallow at the beginning and shallow at the top. So we need to multiply green dashes times solid black, right? So in the place where this function has zeros, in the to the right from the middle, at the beginning of the box and at the end of the box, right? What will be the sign in the range from first 0 to second 0? Plus and plus will be plus. What will be the sign between second 0 and third 0? Plus and plus will be plus, right? Where it will be higher? to the left. So it will be unsymmetric two-hump hammer, with bigger hump to the left and smaller hump to the right. So what computers does in fractions of a second, we did in like 5 minutes. So we can do things. Now let's go and open the quarter period. If one carefully expands this cosine square, it will have 0 exactly in the middle, and if we multiply it by, if we shift it up and take square, it still will have the 0 in the middle. So it will be symmetric candle. Well, since I'm not an artist, you can tell that it is a symmetric frog or whatever. And if you look the snapshot at the half period, we will repeat the same protocol, repeat all these exercises, and see that the 0 will be shifted to the left. And then, as humans, we can assume and understand that there will be nothing except motion from this shape to this shape to this shape as time passes by, right? And if you go further, then it will go backwards. And any figures in the field will be, you can just artistically interpolate it. So the middle point will shift either to the left or to the right, but nowhere it will hit, it will be non-zero at the wall. Nowhere it will get rid of the second small hump, and nowhere it will condense in the ideally determined position, where ideally determined position will be if the peak is infinitely high. That will be always distributed. So it kind of agrees with our uncertainty principle. So position and velocity are not known for sure at the same time. And as here are these figures. But since we do have computation, we can look at this interpolation in a little better way. So we do see that theoretical predictions were matching computational procedures. So it shows 2 humps, but the middle point travels in the maximal point where it is more probable to find electron oscillates forwards and backwards. I probably will not, well, we may try to do it later, but finding expectation value as you did in the overview, you completed in the homework, is a little longer and more challenging. Still, computation is more pleasant, and you get the conclusions and answers to the questions almost immediately compared to little exercise, theoretical exercise. Okay, I think we are done.